I'm going to start to catch up to you guys. This first one, the rule would work, but why is it so much easier than applying the rule? What's nice about 5x to the fourth, it would come from x to the, and the 5 would have come down. So you just were like putting x to the fifth back together. If you did the rule, it would be 5x to the fifth divided by 5. The 5's canceled. You get x to the fifth. The rule still works. There's just a shortcut here. The 5 just goes back up. Bam! That kicks ass. What about the rest of it? Minus 3x plus c, kick ass. I like it. I didn't give you any more information, so you can't figure out what c is. So anything that looks like that has a derivative of 5x to the fourth minus 3. This guy, we just did a problem like this, so hopefully this wasn't a problem. Where does he come from? Make sure that's big ass f. ln of absolute value plus c. Kick ass. Something that's almost always true is before you try to do something to a problem, you simplify the problem. So what is tangent theta divided by secant theta? What's tangent theta? That's right, sine over cosine. And what's secant theta? One over cosine. So divided by 1 over cosine is times cosine. So really I'm working with sine theta. So what's big ass f of theta then? You gotta be a little careful. Yes, negative cosine theta plus c. Does everybody see that? All I did was simplify to see what the function really is. Tangent theta divided by secant theta? Shit, let me just say sine theta, because that's what the hell that is. Okay. So on part D, let me do it the long way first. Then we'll do it the shortcut. And the shortcut might actually help you figure out f. So the long way is related to what we did here. I just simplify the problem I'm given to work with first, so then I can work with it easier. And I really want to make this point. Antiderivatives do not have product rule, quotient rule, chain rule. They have answers to those. Because what's antiderivative? Undoing something. So there's no product rule for antiderivatives. There's how to undo a product rule to come back to where you were. But there's no product rule for, you can't take the antiderivative of one times the other one plus. No, it doesn't work the same way because I'm undoing what I did. So you don't have the same kind of rules. So I can't just, do each piece separately. But if I simplify this first, multiply this stuff through, now I've got a nice polynomial. Should be relatively easy to work with. This first piece is nice. Same idea as this one's up here, right? That 6 just goes back up. What about this guy? What I always do with this, x cubed would have come from x to the fourth. What has to be here, so when the 4 comes down to get 36? 9. The rule would still work. If I did the rule, it would be 36 x to the fourth divided by 4, and you get 9, but you can also think about it more directly. There had to be a 9 there, so when the 4 comes down, you make 36. Maybe. And then this guy's not too bad. This would be x squared, so it would be here, so double that would be 54. 27 plus c. Now real quick, let me show you the shortcut. Here's a shortcut for this. Where did this come from? It must have come from x squared plus 3 cubed. Do you see that idea? I'm not done yet. I've left some room for adjustment if necessary. What's the derivative of this? Let me see how far I am off from this. If I'm missing an x, I'm screwed. But if I'm missing a number, I'm okay. What's the derivative of this? It would be 3 times this times x squared, right? Sorry, times 2x. Derivative of x squared. So if I take this guy's derivative, I get 3 times this times 2x, which is 6x. Oops, and this, of course, goes down to 2, which is 6x, x squared plus 3. So this is plus c. That is the answer. Will that kind of thing always work? No. Are you able to tell when it will work right now? No. But I want to start to show you the things to look for. I knew this might work because the derivative of the inside is out here. Off by a constant, maybe. But that power of 3 came down and made it work perfect. Now, if you multiply this shit out, whoops, this here, you'll end up with this. Believe it or not. Okay. Let's see, continuing on. What about this guy? Where'd secant squared come from? Secant squared comes from what? Is the derivative of tangent. So I know it came from this. But when I take this guy's derivative, what's the extra piece that comes out? Poor little x. If I take this guy's derivative, I get secant squared this times pi. I don't want a pi. So I divide by pi. You can either put a 1 over pi in front, put it over pi, whatever kills that pi that wants to come out. If you get what I'm saying, the stuff we'll do for the second half of the semester will make a lot more sense. It'll be a lot easier. This idea of, I know secant squared comes from tangent. What's it off by? A constant. Good. I can adjust that easy. Stupid pi. I don't want you pi. Let me divide by pi. So if I take this guy's derivative, it will be this, because I'm killing the pi that wants to come out that shouldn't be there. I love this idea. I love it. I know I'm weird, and I don't care. It's a beautiful idea. There's dumb ways to take care of this, meaning other ways to do this that I don't agree with. We'll see. This guy, I'm telling you, you have to do it the shortcut way. So let me rewrite this. This is really bad form. All right, so that's what that looks like, right? So can anyone tell me where something to the negative 1/2, where would that have come from? Whose derivative would I take to get there? So to the 1/2, I love it. So if I take a derivative of x to the 1/2, it becomes something x to the negative 1/2. That something is a constant, doesn't really affect the idea. So let me guess. Let me just take a guess. That it came from x squared plus 3 to the positive 1/2. And then I can put my plus c. And then let's check it. Does everybody see where the guess came from? And why do I feel like the guess might work? This is the key thing you've got to start looking for. I know this has a chance to work because the derivative of this is out here. Minus a constant. And again, constants don't change the process. I do have to make sure they're right, but they don't affect what I'm doing. They just come for the ride. If that x on top was just a 1, there's a method you learned in Calc 2 to do this, but we would not be able to do this in this class. If it was just 1 over that, screw that. So let's check. I haven't checked yet. What's the derivative of this? From what I've written, I would get 1/2 x squared, become squared, to the negative 1/2 times 2x. 1/2 of 2x is x. Isn't that what I had to begin with? So that's the answer. This is the function whose derivative is the thing I was given. So I know that's the antiderivative. So the generalization I can make is if you're taking the antiderivative of a function that would have a chain rule piece to it, the chain rule piece has to be there for it to work. So x squared plus 3 would have a chain rule, 2x. There's an x there. It has a chance to work. Okay. All right, this next one's not nearly as bad. The big ass f should be relatively easy to find. What do you get? Yeah, you get sine 3x, but then a 3 would come out you don't want, so you take 1/3 of that. And now you just use that information. So f of pi over 6 equals sine of 3 pi over 6 over 3 plus c, which is supposed to be 1. So I use the information that I'm given, and now I can solve for c. What is sine of pi over 2? Right, is that what I get right there, right? Sine of pi over 2 is 1. So I get 1/3 plus c is 1, so c must be the other 2/3. Now don't circle that. What's your answer? Kick ass. Put back together. The answer's got to be the antiderivative. You figured out what c is. Put it in there now. I like it. I like it. How do you check your work? Take the derivative. Okay. So what we're going to do is going to seem, well, we're going to seem to take a diversion. We're going to talk about how to find areas under some given function, which is kind of huge. Has anybody taken statistics ever? Anybody? A few of you guys? There's the whole thing about the normal curve. And some teachers, like me, we use a chart and you got to look it up to get the area. And it's made from calculus. Calculus, one huge thing calculus does is it's able to find the area under some function no matter how freaky it looks. I like it. So one thing I love to do is once we get through this, all of this, the area and how is it related to the antiderivative, I like to take functions that make geometric shapes that we're used to and show that it comes out to be the area I would get if I just use freaking geometry. I like to do that because I'm crazy. But these are able to handle whatever the hell this function looks like. So that's kind of powerful. So here's the idea. In fact, I want to start with something that is going to be really, really basic, but you might never have seen it before. What's the area of a circle? Now, I know you've seen the area of a circle before. It's not the part, but I don't know if you've ever seen why the area of a circle is what it is. Who worked? Were you working? Yes. What's the area of a circle? Yeah, pi r squared. Now, I could prove that using calculus once we learn all of it, or I could just prove it more directly. And I could do this with the trapezoid too, but most often the trapezoid people have seen more often. Here, this is the one that people probably have never seen. Have you ever seen the derivation of why that's true? I don't know. You're like, maybe. I don't know. Give it to me. All right. This so kicks ass. Can somebody tell me how far this is? How far is that? That's the what of it? Circumference. And what's that? 2 pi r. I think I heard that earlier, but I just want to make sure. 2 pi r all the way around. So how far is it? This much. halfway would be pi r. I love it. Okay, stay with me. Right? Nothing amazing there. I'm using circumference, right? The head of the round table. Now this is so freaking cool. Let me chop, so let me redraw this bigger. So let me chop this circle right down the middle. Right? I'm going to chop it. Chop. And then I'm going to do, I don't know if any of you have ever done this. You ever done the where you have the string of dolly, the string, you know what I'm talking about, the paper. You cut it, and you open just all these string of dollies holding each other's hands. Have you ever seen that before? You have no idea what I'm talking about. All right, some of you guys know. All right, I personally have done that. I don't know what shape I made. So here's what I'm going to do. I'm going to cut from the center. I'm going to cut, but not through the outside. So they're still connected. So I'm chopping, and then I'm stopping, and then I'm chopping, and I'm stopping, I'm chopping, and I'm stopping. And I actually do a lot more triangles than that. Let me just draw that many, because I don't want to draw one. So what's happening? And then I'm going to open that sucker up, so it looks like, oh, right? So it looks like this. I'm going to take this, and I'm going to open it up, so it looks like this. Chop, 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 chop. Right? How long is this? What's this? Nothing amazing there. I took it and I opened it up. So it's got to be this, which of course is pi r. Now let me do the same thing to the bottom and open it up and shove it in there. Now they're smaller, and the more triangles I do, the more this approximates a rectangle. With just this many triangles, it's not really going to, it's going to be like a parallel. It's going to be slanted on the outside. Are you guys semi with me? But if I did like 3 billion triangles, and I fit it in there, it's going to make, to my eye, a perfect rectangle. How tall is this? How tall is it? R. What's the area of that rectangle? Pi r times r, pi r squared. So one way you can analyze the areas of something you don't know is to reorganize it into a shape you do know. So with trapezoids, I'm not going to do trapezoids, but I don't know if you guys remember, with a trapezoid you can make 2 triangles. Add the areas of those triangles and you get the trapezoid area formula. All right. This is a little bit more interesting, and also, has anybody ever seen that before? Anybody? Yes? A couple of you guys? Okay. You just got me and my crappy ass drawing, but hopefully it still makes sense. All right. It's real. That's, to me, that's one of the coolest freaking things. That's basically what we're going to do to start with, is we're going to cut functions into little rectangles, find the areas of those rectangles, and add them up. Are they going to be the exact answer? No. So for example, let's do a quick example. This is almost too nice to believe to start with, and then it very quickly gets, a little more disgusting. Oh, let's see. I don't need you anymore. Get out of here. Oh, no. All right, so let's do this. Let's say, what you got, Jeff? Yeah, let's do, look at this, I'm sorry. Put a 4 there. All right, so I got that, put a little 4 there. I just wanted to give myself some more room to work with. Okay. So if I try to sketch this, let's see. Have I made a decent function? I don't know, Jeff. Probably not. Yeah, okay. Let me make one little adjustment. Try to make a nice function to start with. Do this for me. Okay. Yeah, that should work. So now I've picked the values of x. So what I'm going to try to do, what the question is really going to ask, is find the area under this function from x equals 0 to x equals 4. So a really good first step is to graph this thing. Give yourself a little picture, right? So let's see. For x equal to 0, y is 0. And for x equal to 4, y is also 0. Are you guys cool with that? Those are the two x-intercepts. You stop there for a second. Okay. Now, for the middle, let's see. At 2, what is this? Negative 8 plus 16 is 8. Is that cool? So at 2, it looks to be an 8. At 1, it's at negative 1 plus 4, it's 3. And at 3, it's at negative 27 plus 36, which is 9, I think. Is it 9? I don't know. Does that make sense? Let me see. So at 3, it's negative 27 plus 36, yeah, which is 9. Okay. So it's like a really... So we could get more involved, but I'm just going to kind of fill us in. Okay. So it probably doesn't look exactly like that, but this is just a quick sketch of what it is. You can look it up in the calculator or whatever. So here's how this works. I want to find the area, but let's say I'm going to use 4 rectangles. So now stay with me. So what I'm going to do is basically this. I'm going to put rectangles in here that have a correct height, so that when I add the areas of the rectangles together, I get a decent approximation for this area. So let me do a really quick little rough sketch here. So just so I don't mess this guy up, because he looks pretty good. So if I put in there rectangles like this, like let's say this rectangle, which gotcha. This rectangle, and this rectangle, right? And I add those rectangle areas up. Isn't the answer going to be close to the area I want? In this case, I can tell it's probably going to be a little bit more than what I want. I like it. How would I improve that approximation? Use more rectangles. The more rectangles I use, the better they fill that space in. So what you should probably realize right now is that we're eventually going to take the limit as my rectangles go to infinity. Yeah, to make this perfect. The only way to make this perfect is to have infinite resolution, which means make my rectangles go to infinity. I like it. I like it. Okay, so here's how this works. There are a couple of choices we can make. What's going to determine the height of my rectangle? Yes. So I could either use, let's do this, I'm going to use right, oh my gosh, poor little marker. Are you working? Let's see, right endpoint. Let's use right endpoints for right now. Here's what I mean by that. The rectangle is going to be from some x value to some x value. The right x value is going to tell me how tall it's going to be. I'm going to use 4 rectangles. Can anyone tell me how wide each rectangle has to be to cover the whole thing? This is a very physical idea. I don't even have to talk about this in terms of calculus. It's just, you know, I got to go from 0 to 4. I'm going to use 4 boxes. How wide does each box have to be so it fills it all in? 1. If each rectangle was 1 wide, wouldn't it fill in 0 to 4? I love it. Is it always going to be all nice? Like, no, it's going to be 0 to 7. I'm going to use 11 rectangles. Too damn bad. But you're going to make little fractions and bullshit. So here's, what is it in general?
the width of my rectangles is going to be b minus a over n. b minus a over n.
If you think about it, it's exactly what you just did. If I had to go from 0 to 6, and I use 3 rectangles, it'd have to be 6 minus 0 divided by 3. Each one had to be 2, a width of 2, so it would fill it all the way in. I love it. I love it. Very physical idea, which is kick-ass. So if I'm using right endpoints, so I'm going to have a rectangle from 0 to 1. I'm going to have one from 1 to 2, from 2 to 3, and then the last one's going to be from 3 to 4. But how tall is that first one going to be is going to be based on its right endpoint. So how tall? So this first rectangle, let's just look at this first rectangle. It's going to be this tall. So the width is always going to be, and the width has a symbol like this. Why does this symbol make sense? What does that symbol mean? Change in x, and that's what the width is. It's how much I'm stepping along the x-axis.
So for us, the width was 1.
So what is the area of just that first rectangle? What is this A1?
Area of the first rectangle is going to be what? It's going to be 1 times f of 1, right? Because f of 1 is how tall it is. And what is f of 1? I think it was 3, right? This first rectangle has an area of 3. I love it. Let me stop there for a second.
I could have made the first rectangle, I could have done left endpoints, and then the first rectangle would have had a 0 area, because the height would have been 0. And we will do that in a minute. So let's see, can you draw the next rectangle in? Hopefully you've got this picture on your paper. Can you draw that next rectangle in?
Sometimes people make the mistake of just making it the same size as that one, but it's supposed to be based on its right endpoint, so it should be this tall.
Let this right now be actually sort of scarily easy. Right? I have warned you, it is not going to remain this nice, because we're going to eventually have to let my rectangles go to infinity, and that's of course going to be a little bit freakadelic, but the basic idea is almost too nice to believe. Just put some rectangles on top, cover it, and then get the areas, and you got a nice approximation.
So what's the second area? Still the width is 1, so it's always 1 times, in this case, f of 2. And what was f of 2?
F of 2 is 8. I like it. And then I keep going. So you know I'm not going to give you a problem where I give you 47 rectangles. That's just busy work to go crazy. I will give you infinite rectangles, but you don't have to do each one then, so that's not busy work.
So A3 was going to go, of course, this tall. And A3, still a width of 1, and how tall is it? F of 3, yeah, they're 1 times. F of 3 was 9, if I remember correctly. So we got A1, A2, A3, we got one more to get. A4, how tall is A4?
Poor little A4.
It's flat.
So look real quick. Up until this point, up until right here, was our answer bigger or smaller than it should have been? It was bigger, because my rectangles are including area that's not under that function. But then this guy, I bet you overall we're under the correct answer.
A4 is 0. So what's the total area then?
Using 4 rectangles, right endpoints, it's an approximation. It's not going to be the right answer, but
Let me call this AR for A right. What do we get? We get 20. I like it. Now let me see if you guys, can you do that all again, but this time use left endpoints. So this time it'll be the first rectangle that has no height. Poor little dude. And then the next rectangle will be this tall. Do you guys see? Now you're going to base the height on its left endpoint. Try it. Try it. Try it. Let me see. I have another color for this. So now this rectangle. So this rectangle is flat. Poor little dude. This one's going to be here. This one's going to be here. And this one's going to be here. The height is now determined by the left side. Where's the function on the left side? Get that right? Yes. Good job, John. I don't know if some of you guys notice. This always happens, of course. You've already done. You can see how we've already done all the work. I mean, this doesn't always happen. This is a nice function. I made the number of rectangles kind of match how wide it was. The width is 1. It's easy. This area of this rectangle is the same as this one was. Right? So A2 has got this area. A3 has got this area. It's the same as that rectangle was. Do you guys see that? No? Yes? Maybe? No? And even if you don't see that, do you guys understand what I've written here? The width times the height plus the width times the height plus the width times the height, all the way out to however many rectangles you had to make. What is x1? It's going to be the first thing I use, depending on which endpoint I use. So this is still just a sum of rectangle areas. That's all that is. So here I'm going to get, again, I'm going to get what's f of 0 was 0. F of 1 was 3. F of 2 was 8. F of 3 was 9. All right, 3, 8, 9, yes. So I still get A is 20. So to get the area of the rectangle, I have to multiply each rectangle by the width. Each width here is 1. So if the width was 1/2, there would have been a 1/2 right there. Right? Is that cool? You guys all right with that? The area of the first rectangle will always be the width times the height plus the width times the height. But the width stays the same. That's why I can factor the damn thing out. So it's still built off of areas of rectangles. That is too nice to believe, but now that you saw the circle problem and I can transform that into a rectangle, it's kind of like what we're doing here. Now, you might be curious, like me right now, about what the exact answer to the area is. And I'm going to go ahead and show you right now how to do that in the calculator, just because. It's always nice to be able to check your work, right? If you have your calculator, here's how you do it. There's a little bit to this that we're not there yet, but I don't care right now. I want to show you how to check your work, because this does get a little bit freaky when things are not so nice. So if I put the function in, negative x cubed, what was it, plus 4x squared? Let me hit zoom 6 so I get a nice standard window. Ooh. Turn the lamp off. Lamp off. Off. There he is. All right, now watch. This is almost too nice. Has everybody got that if you want to play along? All right. There will be a symbol we will introduce when we do limit. What am I going to do? I'm going to let the limit as what goes to infinity. To make this perfect. To have infinite resolution. What am I going to allow to go to infinity? It's kind of hidden up here. I didn't make a huge deal of it. Well, what represents the number of rectangles? N. So eventually I'm going to have some function of n. I'm not going to put a number here. I'm going to leave n here. So then I'm going to get a function of n. I'm going to let n go to infinity. And when I do that, I'm going to represent that with this symbol. So you might have run across this symbol somewhere. If you've had calculus before, you've seen it. But what this really is, that symbol, it's really an elongated S, and it just represents the infinite sum. So if I let the number of rectangles go to infinity, I still have to add up all their areas. So I'm going to have an infinite sum of areas. So somebody back in history, I think it might have been Newton, I don't know. I think it was Newton. He said, well, why don't I just use a really long, kind of elongated S to represent the infinite sum? And that's exactly what that thing is. It's kind of freaky. But, symbols don't really mean anything by themselves. I could have made it anything they wanted to, but I wasn't there to make suggestions. So if we do this, number 7, now watch. 7, lower bound, lower limit, 0. I'm going to go from 0. Upper limit, 4. Now watch what this does. This is so kick-ass. Shoop. There. So the actual answer is 21.3333. And what did we get with only 4 freaking rectangles? Our approximation was 20. That's already really good. Now why did I only need 4? Because the function is so nice. Doesn't go crazy, right? If I had some function going and saying I use 4 rectangles, I'm not going to get a very good answer, probably. Okay, maybe you guys are with me. I like it. So that's a beautiful, I love the way this represents the answer visually. It shows you the area you're talking about. So if I did a process, if I did 8 rectangles instead, I have a little more work to do. How wide would each rectangle be then if I had 8 rectangles? They'd each have a width of 1/2, so there'd be a 1/2 sitting out here. And then if I did left endpoints, it'd be f of 0 plus f of 1/2, plus f of 1 plus f of 1/2, blah, 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 blah. Yes?
So if you're doing right, you can start at f 1/2.
Yes, beautiful. I love it. So there's got to be a rectangle. In that case, are you guys kind of with me? 8 rectangles, the width would have to be 1/2 to fit the 8 rectangles into a space of 4. Does that make sense physically? Stay with me now. It's not that big of a deal. It makes good physical sense. That first rectangle has to exist between 0 and 1/2. So the height's either going to be based on 0 or it's going to be based on 1/2. I love it. That's all that boils down to. And if you have to do left endpoint and then right endpoint, you're always going to have a bunch of the work done already on the first go-round. Here it worked out beautifully because both sides, both ends were 0.
So we didn't have any extra for any. I don't know if you. All right, let me give you this. Oh, I already gave it to you. So if you flip that, did I give you this one yet? No. Did I give you this one yet? What's this one? Oh, here we go. You flip this guy over. Yeah, this is where things get freaky. This is letting the number of rectangles go to infinity. Let's not do that, Jeff. If you flip this practiced one over, we have a problem on the back here. Let me just make sure that everybody remembers this notation. Gotta take this away. See if you guys remember this. So when I have a long-ass sum where it's basically the same idea in each piece, I can use summation notation. So hopefully, you guys have to have seen summation notation already. So here's what it would look like. So what's each rectangle look like? What's each area of the rectangle look like? The width of the rectangle times the height of the rectangle. I'm going to do it from the first rectangle to the last rectangle. So everybody, please, dear God, it's okay if you haven't, it's not your fault, but it's bad. So hopefully everybody has seen this notation before. Let's just focus on that notation for a minute, just in case it's been a while. Not going to really come into play in this problem, but it's going to come into play in the next section immediately. So you might as well look at this. If I had this, can you guys figure that out? Let me turn you around. That's what we're just talking about there. How many terms will you end up with to add? Do you see how I is sort of the summation variable? It's what's going to vary. So at first I is 1. So when I is 1, I get 1. Plus, because that's what the symbol means. Then I'll let I become 2. So the step is assumed to always be 1 unless it states otherwise, and that's where things get freaky, but we're not going to do it. So let I be 2, and that of course is 4. And let I be 3, that's 9, and that's where I stop, because that's where it said to go to. From 1 to 3. And then I just add those together. Cool? So that symbol, that notation is pretty straightforward. In case you're curious, there is a symbol for repeated multiplication. And it's what time is it? Oh, it's an uppercase pi. So this would mean let I be 1 multiplied by let I be 2 multiplied by let I be 3. I didn't learn this until way later, so I like to show it immediately. If you know this symbol, you should also know, there is a symbol for repeated multiplication, just like for repeated addition. Just so you know, it's not going to show up in this class besides right now. Yes?
It also works way around where I is 10 and the top number is 1, correct?
Yeah, you in general, you don't like to do that with summation notation itself. When we take it to that symbol on the calculator, so this is this where I go to infinity. So then if I had from 3 to 1 of stuff, that would be negative from 1 to 3. It's the negative of it. Summation notation, it's basically defined to be from smallest to biggest. Yeah. There are some little things you can play with it, but it's got to always come back to that definition. Maybe. So go ahead and try that problem out up there.
The width is not going to be 1.
Giving you the graph so you can draw right on that sucker. Now, on a test or a quiz, if they give you the graph and they say put the rectangles in, don't just throw rectangles. They have to be in the right place. They have to have the right height.